Here's a trap that catches every programmer. You have a slow program, you look at the code, you have an intuition about what's slow, you optimize that part, and the program is still slow because you were wrong. The solution isn't better intuition, it's measurement. Go's profiling tools tell you exactly where CPU time goes and exactly which code allocates the most memory. This episode covers how to collect profiles, read them, and act on what you find. Go ships prof in the standard library. No external tool, no vendor dependency. The runtime/prof package gives you programmatic control. Start a CPU profile, stop it, write a heap profile. The net/http/prof package registers a set of HTTP endpoints on your existing server with a single blank import. After adding import net/http/prof and starting a debug HTTP server, you get a full profiling suite at localhost 6060/debug/prof. Hit/debug/prof/profile. Seconds equals 30 for a 30-second CPU profile. Hit/debug/prof/heap for a heap snapshot. Hit/debug/prof/goroutine to see every goroutine stack. All accessible from a browser or Go toolprof directly from the URL. The HTTP approach is ideal for production services running in staging. You can collect a profile while the real traffic is running without redeploying. For scripts and batch programs, the programmatic approach with prof.startCPU profile is cleaner. Programmatic CPU profiling. Create a file, call prof.startCPU profile, F. Run the work you want to measure, then prof.stopCPU profile. Always defer stop CPU profile. It flushes the profile data to the file. If you forget, the file is empty. The profile records where the CPU was executing at a high sample rate, typically 100 times per second. After enough samples, you get a statistical picture of where the program spends its time. Go toolprof CPU.prof opens an interactive session. Top shows the hottest functions sorted by flat time, the time the function itself used, excluding calls. Top, cum sorts by cumulative time, the function plus everything it called. If a function's cumulative time is high but flat time is low, it's a coordinator that delegates expensive work. List funcname is the most actionable command. It shows the function's source code with per line CPU time annotated on the left. You can see exactly which line is hot. Web generates a flame graph SVG in your browser, particularly useful for understanding the call tree visually. For tests and benchmarks, Go test, bench equals. Qprofile equals CPU.prof collects a profile automatically during the benchmark run. The profile is scoped exactly to the measured code, no startup noise. Memory profiling captures a snapshot of heap allocations. The programmatic approach, run the work, call runtime.gc to flush dead objects, then prof.write heap profile, F. The GC call before writing is important. Without it, the profile includes objects that have already been collected, inflating the numbers. Go toolprof mem.prof opens the memory profile. Two views matter. Allocspace shows cumulative allocations since the program started. Everything that was ever allocated, including what's since been collected. This finds allocation hotspots. Functions that allocate a lot even if they don't hold it. Inuspace shows only what's currently live in the heap. This finds memory leaks, functions whose allocations stick around. To find a memory leak, take a profile early, take another profile after load, compare them with Go toolprof, base equals heap1.prof heap2.professor. The diff shows what grew between the two snapshots. For benchmarks, Go test, bench equals. Memprofile equals mem.prof. Benchmem collects both a memory profile and the allocs/op and bytes/op numbers in the benchmark output. You get the high-level numbers from the benchmark and the detailed breakdown from the profile. The most productive workflow combines benchmarks and profiles. Write a benchmark for the hot path. Run it with Qprofile and Memprofile. Open the profiles in prof. Find the top allocator or CPU consumer. Make one change. Run the benchmark again. Compare. BenchStat formalizes the comparison. Run benchmarks 5 times with count equals 5 before your change. Save the output. Make the change. Run again. Pass both outputs to BenchStat. It computes the percentage improvement and the statistical significance. A 40% reduction in NS/op that's statistically significant is a real win. A 5% change that isn't statistically significant is noise. The discipline is one change at a time, measured before and after. Multiple simultaneous changes make it impossible to know which one helped. Go's garbage collector uses a tricolor mark and sweep algorithm that runs concurrently with your program. The 3 colors are states in the mark phase. White objects haven't been seen. Gray objects have been found, but their references haven't been scanned yet. Black objects are fully scanned and reachable. The GC starts a brief stop-the-world pause to enable a write barrier and mark roots gray. Then it runs the marking phase concurrently. Your program keeps executing while the GC scans objects. Another brief stop-the-world finalizes the mark. Then the sweep phase frees white objects concurrently. The result: GC pauses in modern Go are typically under a millisecond. You won't notice them in most applications. Where you might notice GC is sustained allocation rate. If you're allocating heavily, the GC is running frequently, burning CPU. GeoGC controls the trigger. The default value of 100 means run GC when live heap has doubled since the last collection. GeoGC equals 200 triggers less often. The heap can grow to 3 times before GC fires. You use more memory but get better throughput. GeoGC equals 50 fires more often, keeps memory lower, but uses more CPU. For batch programs that exit immediately, GeoGC equals off disables GC entirely. Fast and no leaks matter since the OS reclaims everything. Stack allocation is nearly free. The runtime allocates stack memory by moving a pointer 1 instruction. When the function returns, the pointer moves back. No tracking. No GC involvement. The cost is effectively 0. Heap allocation requires the allocator to find a free block of the right size, record the allocation for the GC to track, and eventually involves GC work to collect it. Not catastrophically expensive, but orders of magnitude slower than stack allocation. More importantly, heap allocations add to GC pressure. The more you allocate, the more frequently GC runs. The compiler decides which allocation goes where using escape analysis. The simple rule: if a value must outlive the function that created it, because its address is returned, because it's stored somewhere that outlives the function, it escapes to the heap. If the value's lifetime is bounded by the current function stack frame, it stays on the stack. Use flags equals m to see the escape analysis output. Move to heap x tells you exactly which variables escaped and why. For common cases that force heap allocation, returning a pointer, assigning to an interface, capturing in a closure, and storing in a data structure that itself escapes. Returning a pointer is the most common. Return and x means x must survive the function's return, so the compiler moves it to the heap. If you need the caller to have a pointer, one alternative is to accept a pointer parameter and fill it in. The caller allocates, the function writes. The allocation happens on the caller's stack. Interface assignment is subtler. When you store an int in an interface, Go must heap allocate a copy to back the interface value because the interface needs a pointer to the data, and that pointer must stay valid after the original int might be gone. This is why passing basic types through interface, or any, has allocation cost. Closure capture. If a closure captures a variable and the closure outlives the enclosing function, the captured variable escapes. This is why range loop captures in concurrent code need careful handling. The variable's lifetime extends beyond the iteration. Pre-allocate slices when you know the final size. Varus int starts with nil, the first append allocates a small buffer, the next append doubles it, and so on. For 1,000 elements, you get roughly 10 allocations. Make int 0 1000 allocates once. The benchmark difference is proportional to the number of elements. Sync pool is Go's mechanism for reusing temporary objects. It holds a cache of objects per goroutine, falling back to a shared pool, falling back to the new function. GC may clear the pool between cycles, that's fine, it's a best effort reuse mechanism. The pattern: get, reset, clear any previous state, use it, put it back. Common use: bytes. Buffer for serialization, sync. Pool to avoid allocating one per request. Strings. Builder for string concatenation. The naive s plus equals part creates a new string on every iteration because strings are immutable. O, n superscript 2. Allocations for n parts. Strings. Builder accumulates into a growable byte buffer. One call to .string. At the end converts to a string. One allocation, or at most a log-n series of doublings. The rule for all three: measure first. Pre-allocating a slice that's only ever 5 elements long is pointless. Pooling objects that are never contended is complexity without benefit. The profile tells you where the allocations are. Then you apply the appropriate fix. Profiling: blank import net/http/prof for live endpoints, or use prof.startCPU profile and prof.write heap profile programmatically. Analyze with gotoolprof top list web. Collect during benchmarks with qprofile and memprofile. Compare with benchstat. GC is concurrent and low latency. Tune with GeoGC if needed. Stack allocation is cheap. Heap allocation adds GC pressure. Escape analysis via flags equals M shows exactly what escapes. Reduce allocations. Pre-allocate slices. Sync. Pool for temporary objects. Strings. Builder for concatenation. Next episode: build tags, embedding files, and workspace mode. This course is based on the complete guide to Go programming. Available on Apple Books and Amazon. Find it at pixelstech.net/book. See you in episode 24.